Today we are going to see elastic load balancers, what group of services it offers, what are the different types of load balancers Amazon offers, and when to choose a load balancer, and why exactly it is required, and what are all the different features that load balancers offers, how to configure, and all those things. So we, as usual, we will see the initial components that makes up the load balancer, and finally we will see all the different building blocks, and finally we'll end with an hands-on demo of the elastic load balancer. So let's go ahead and quickly see what group of services elastic load balancer forms part of. It is the networking part of the service that Amazon offers. So ELB forms part of the networking group of services, and we will start looking at what are the why a load balancer is required and move forward from there. So typically what happens is when you are running an EC2 instance or a web app application or a web server without a load balancer, your user hits your server directly. So this is the typical logical flow of the network traffic looks like. But what happens if this instance goes down? The IP address or the URL that you attached with this instance, you are going down along with the instance. And if you're going to bring up a new instance, then you need to attach the same IP address so that you don't have to communicate to all the people who are accessing your web server, so that they don't get different URLs every time your server goes down. So there are some difficulties when you have no load balancer in front of it, because whenever you want to change something on the back end, you want to communicate with your end user also and inform them of the changes, so that they know the URL is going to change and they have downstream impacts as well. But when you introduce a load balancer, what happens is the end user is going to always have one entry point to your application, because whenever the instance on the back end that goes offline, you are going to change only that particular instance. Say for example, this one goes offline, you are going to replace it with a new instance, and your load balancer will start sending traffic to the new instance. And your load balancer itself is designed to be highly available by Amazon, because it runs multiple instances of its own on multiple subnets, because by design it is like that. So your load balancer is designed to be highly available and within the same region. Your load balancer cannot send traffic to multiple regions. It resides in a particular region only. So if you have instances spread across multiple regions, then you will need a load balancer in each of those regions. So that is how your load balancer removes the headache of communicating with your end user and providing a single entry point for incoming request, and manages multiple EC2 instance on the back end as well. So this way management is easier, and not only that, a load balancer is designed to avoid DDoS attack. Nothing but if somebody is flooding your server with a lot of requests and not waiting for a proper response from the request, and just keep on flooding, your server will be overwhelmed by all those responses and will not be able to serve legitimate traffic. That is a typical DDoS attack. And DDoS is, if you are not familiar, it is a dynamic denial of service attack. That is what quite often happens nowadays when the web is overwhelmed with unnecessary requests without waiting for a response. And the DDoS attacks are designed to be thwarted or mitigated in ELB, and Amazon takes care of all those problems. So you just provision the ELB in front of your EC2 instance, and you increase your service availability by having an ELB in front of your EC2 instance. So not only those features, Amazon gives you some additional features also. It is elastic. As your traffic grows, your load balancer also handles the additional capacity. And as I was talking about the security part of it, it can handle DDoS attacks. It can handle SSL traffic. It can do SSL negotiation or dropping the SSL at the load balancer level. And it is integrated with multiple services. So you can not only put it in front of your ELB, you can front end the load balancer with a Route 53 also, so that the URL will be your company domain in www.abc.com will point to your ELB and your ELB. We are going to call the load balancer as an ELB here, that is Elastic Load Balancer. So the ELB will indirectly point it to the EC2 instances. So it is not, it is integrated with many of the Amazon services, so it is very easy to configure a load balancer in front of an application server or in front of a web server or configure it for an FTP server or SFTP server. It's up to you how do you want to configure it. And there is a small cost associated with the load balancer for the traffic that passes through. So when compared to all the other load balancers available in the market, if it is for FY, Palo Alto, or any of those load balancers or network devices you use, Amazon's price is comparatively good. I'm not going to say this is the best pricing that you will be getting for your money or best product that you're going to get. You need to choose what is the best for your company and your environment and recommend it. And I would say it is very competitive, and because the headache of management of the device is taken care by Amazon, the software and the hardware is taken care by Amazon. It's a software as a service, or load balancer as a service. So if you calculate all those things, its cost is quite effective, I would say. So a typical load balancer architecture we are going to see now. Let us say on the right hand side you see a typical VPC where there are two availability zones, and let us say for simplicity reasons we are going to look at only the web subnets, that is web server subnets or public subnets in other words, and you have two EC2 instances. So, and then you have a load balancer VPC. Now, it is always a good practice to put your load balancer into a separate subnet of its own and security group of its own. But in this case, they have gone ahead and created a separate VPC only for the load balancers and created a separate subnets for the load balancers and security group and everything. So they typically sit in front of your web servers as shown in this architecture, and both of them will be connected to each other. So as I keep saying, a load balancer is spreads across two subnets. So if you create a single load balancer service on a particular region, automatically one for each region is created, an IP address or network interface is created in each region, and traffic is forwarded to the load balancer. So it is a logical setup here. Typically, it is only one service you set up for one region, but logically it is available for both the regions, I mean both the availability zones. And in front of it you usually put a Route 53, that is our DNS service. So if you're having something like a www.abc.com, and that abc.com will send traffic to your load balancer, and in turn the load balancer will say, okay, this is looking for IP address or subnet which is in this availability zone, and this request is for 1B availability zone, so let me send the traffic here. So this is our typical architecture or a logical view of your load balancer looks like. So some other features, we need to learn some of the components that make up the load balancers. So we will see that in a short while. So a load balancer typically balances EC2, and it can support private and public traffic. What it means is you can have a load balancer for internal traffic also. It is not necessary your internet facing applications should be front-ended with the load balancer. Your internal applications, say for example you're running an intranet on your company's intranet is on AWS. It is not internet facing only for your company employees, and almost everybody is logging in through your home page, for example. Then you need a load balancer in front of your home page so that the web server that is running your home page is not overwhelmed by all those requests. You spread your web server by using auto scaling, and then you put a load balancer in front of it and point your domain name at your load balancer and give that URL to your employees, and everybody will be logging in through that private IP address or a private URL, and they will be accessing your application. And you have full control over the load balancer security group. You decide which port you want to open, which port should be connecting to it, what port it should forward it to. Say for example, you can open it for port 443 in the external world and drop it at port 80, or open it for 8080 to the external world and drop it back to 80. You can have any number of combinations that you want, and you decide what you want to use. And as I keep saying, it is integrated into multiple services, not just VPCs, not just subnet level, and it is integrated with Route 53. It can be directly talking to an EC2. It can be front-ended with many things, not just at the network level. So load balancer is feature rich, we can say, when we're talking about AWS ELBs. And not just that, your load balancer can also do health checks. For example, if you have a particular URL, it can keep checking for whether the URL is available, and if the server that is serving that particular URL, say for example abc.com/example.jpg, and this image is very very important for your site, and you keep on trying to access this image or corporate logo.jpg. If for some reason that the image is not available, Amazon ELB will mark that instance as impaired or failed, And usually this notification is sent to CloudWatch, and CloudWatch will send it to autoscaling, and autoscaling will try to start up a new instance in that case. So it can do health checks, and it will shift the traffic from impaired or failed instances. So let us look at how it exactly works. So we have three instances here. All are serving very good traffic. All of them, let us say the health check is green as shown in the indicator on the right hand side. Everything is great. And suddenly we find that there is some problem with one of the servers and its CPU has gone up. If you're not noticing, you can see here the instance number one has gone up with a very high CPU here, and load balancer will take notice of that, and what it does is it immediately triggers a notification to the other two. It triggers a notification and stops sending traffic to that instance, because the latency will increase if it keeps sending traffic to that instance. So it tries to rebalance the traffic and it will send it to the other servers. So as you can see here, there's a slight increase in traffic on this one. As you can see, there are two green bars here, and slowly the traffic will get increased to the other one as well. So you can see that the second one, the middle one, also has two green bars right now. So the traffic is been rebalanced to the other two active or healthy instances in this case. So after some time, let us say the traffic is, the instance recovers or auto scaling fixes the instance with a new instance, and a new instance is available, then load balancer will start sending traffic to the first one, and then it will do the rebalancing effect. So slowly you can see the traffic disappearing from the second and third instance, and all of them are having equal load right now. So this is how a typical load balancer looks like. So one server goes wrong, it rebalances the traffic and things like that. If it is an availability zone failure, we will see that in a short while. There is another nice logical view of how an availability zone failure is handled. So we spoke about the health checks. It can do health checks for TCP level. It can do health checks at HTTP, HTTPS level. And now there is another load balancer called an application load balancer. We will see that in a short while. It can do health checks at a URL level also. It will try to see whether /login.html can work, or or say for example a different URL or a subnet you have. It can check for those things also. And you can customize the frequency, failure threshold, and what is the successful response code, whether it is HTTP 200 is your successful response code, or some other HTTP response code is your success. You can decide all those things. And for whenever there is a health check failure, you can check the reasons for the health check failure also using an API call. So you can programmatically manage your ELB as well. That is what you need to understand. Idle timeouts, this is another interesting concept. So first we are checking the health, and now we are trying to find out whether the server is having too many connections. Should we drop those connections when there is an idle time? Say for example, the customer is talking to your web server. He has made a request, and for after making the first request, that customer is not talking to your instance for, say for example, 300 seconds. You want to drop that connection because you don't want to keep those connections active. Otherwise your bandwidth or your throughput is going to be clogged here. So what is the default time? It defaults to 60 seconds, and you can set it to anywhere between 1 to 300 seconds. So after the idle time is over, the load balancer will drop that connection, or in other words, close that connection, and you have the flexibility to configure it to whatever time you want. That is what idle timeouts means, and this way you can keep your server serving maximum amount of traffic and dropping the inactive connections. If there are any Indians available, and if they are trying to book an Indian Railways ticket, they know that if they are idle for some time, say for example 5 minutes, the server will lock them out. So those kind of configurations are definitely possible by using idle timeouts, by using load balancer. It's just an example to understand. I'm not saying IRCTC is using AWS and ELBs, but it uses a similar concept here. So moving forward, how do I configure my load balancer for listeners? What traffic should I listen to? What protocols I should listen to? What port should I listen to? That is what you configure in your listeners, and you can have up to 10 listeners for your load balancer. Say you can listen for port 80, port 8080, or you want to listen to HTTP port protocol, or you can listen to HTTPS protocol, or you can listen to SSL also. SSL, that is HTTPS. You decide what protocol you want to look for. And you can have your routing rules also configured. As I said earlier, you can listen for 443 and send it to your server at 80 itself by dropping the SSL at the load balancer level and reducing the workload on your web server. It is for application people, it is usually called as SSL termination, where do you want to terminate it. If the certificates are managed by ELB or Amazon, it will can be terminated at ELB itself. If the certificates are managed at your web server, then you will forward it to at 443 itself to your server. So that is the routing rules we are talking about here. A little bit more on the rules. If some people find that this is little bit in depth on application side, when you are trying to configure it for a simple application like a web server, you will understand what is this concept of health check, what is the concept of idle time, what is the concept of routing and the rules. It's very simple when you do it. This is on the conceptual side or the components that make up the load balancer. So just stay with me when we are doing the demo. You should be able to have a good grasp of all these items. When I say rules, think of it in a logical way. Say, for example, if a particular URL is matching, I wanted to send it to a particular server. For example, I can have a web server which is serving only style sheets, or I can have a web server which is handling all my image requests, or I can have a web server which can handle only my login atoms. So login will be happening at a different server, payments will be happening at a different server, and images will be coming from a different server. So all these kind of rules, I can have a pattern matching with an URL. I mean, I can write my URL appropriately so that in my load balancer, I can do a pattern matching and send the appropriate request to the appropriate destination server. So that I can increase the throughput of my web server and application servers, because static image, static artifacts or static objects need not be served from my application layer. I can serve them from my CloudFront or S3 or any other location. Only the dynamic content that needs to be generated for my website has to be coming from my application server. So if I have a pattern matching available, I will appropriately reroute the traffic to that destination. And if you remember, I have flexibility of forwarding the rules by using different listeners. So based on the listeners, I will configure the rules, and the rules will send it to the appropriate destination as well. And there are multiple target groups. You can, as I said, the target group can be a static content target group or dynamic content target groups. So that is what we are going to see next. What are target groups? Actually, the logical load balancing target can be an EC2 instance or a microservice or a container based application. As I keep saying, your destination can be anything. It not necessarily needs to be an EC2 instance. It can be a static content service or an elastic container service or some other third party application also. It's just another URL you are going to forward to. In other words, the target group can be anything. And again, once again, multiple ports are available. You can have a wide range of ports you can forward it to. There is no hard and fast rule saying this is the port that you can use. And you can have the same target registered to multiple target groups. So in other words, your EC2 instance can receive traffic from multiple load balancers also. So that is also possible to configure. So some design practices when it comes to load balancers, when you're trying to build a load balancer, always use multiple availability zones. The reason is when you're trying to create a load balancer, it asks for subnets. Sometimes I see people creating subnets in the same availability zone and trying to call it as a high availability. That is not the case. If you want really high availability, you need to use both the ACs or as many ACs that you have, and it is always good to create subnets on both the ACs and use those subnets for your high availability. So don't think that it is easy to create different subnets in the same availability zone and try to call it high availability. It might give the look and feel of an high availability, but it is not the case. And always associate two or more subnets, as I was talking, in different zone with the load balancer. That creates your resiliency as well. In case one of the ACs goes down, you have a resiliency in that case. So as I said, here is a logical view of things. Once again, we are talking about two availability zones, two load balancers in front of it, and Route 53, your customer is there. And let us say you have an AC failure right now. So one of the AC is completely unavailable. So what happens in this case is automatically the load balancer will reroute the traffic to that EC2 instance which is already available. This is the logical view. What in the background, it also triggers a notification to your CloudWatch, and the CloudWatch talks to autoscaling, and the autoscaling talks to your EC2 instance and creates another one. And then what happens is your server is brought back online, and then your load balancer is rebalanced. So this is another example here. Let us say one instance is heavily loaded. As you can see, the top one, you can have different combinations. Let us say the instance in the top is a C4 or M4 or very good server, whereas you started some lot of smaller instances on the other availability zone, say for example T2 micro. But although that is server is a bigger instance, you are seeing a lot of CPU traffic or network latency there, and you can see the performance metric is really all over the chart here, and it has already gone to the red level. That is a warning level that you can see there. So the load balancer will be cognizant to this effect, and as you can see at the top, there is an imbalanced instance capacity in this case. So there is something called cross zone balancing that is available in your load balancer. It is just another service. You just have to put a tick mark. So what happens when you do is, you can see this, both these arrows, this load balancer is trying traffic here and this one is sending here. But when you enable cross zone load balancing, what happens is they send the traffic to both the destinations. That is, all this traffic is possible. This load balancer will talk to this guy and this guy as well. So this way what happens is your traffic gets rebalanced, and you can see here the load on this server comes down and this server starts picking up the additional traffic here. So that is what cross zone load balancing means. In other words, you send the traffic to all the availability zones that you have instances on. And finally, this is just a more text on the same thing. There is no additional charges for cross zone load balancing, and automatically the DNS for the new instances are cached on your load balancer. So it doesn't have impact or latency because of you having cross zone load balancing. So it's a very good feature if you have multiple instances, and if you are going to think of different instance types for different availability zones, cross-zone load balancing is another good feature that you can use without any additional charges. So this is a very good logical view of things that we all spoke about. So at the top you have your load balancer, and then you have your listeners, and the listeners will have different rules. As I said, there's a default rule, and then say I want to handle traffic for images, that is /images. It can be anything before that, and if I have /image anywhere in my URL, send it to my target group too. So these two EC2 instances that you see in the middle is only designed to serve image traffic. And say for example, this default is something like a login page, and this default is listening only for payments page or something like that. So you can have your load balancer distribute your traffic to different instances for different purposes. So all that concept that we spoke about, listeners, rules, and target group, is identified here. This is how the logically it looks like. Although all the functions are, this entire functionality is part of the load balancer service, but logically that is how it looks like. And this target group is more logical grouping. It is not a placement group, or it doesn't enhance anything. It is just a logical grouping of servers. Say this guy is for a login, and this guy is for images, and this guy is for payments. I mean, this target, I'm talking about target groups here. So it is absolutely left to you how you want to group your instances and how do you want to configure them in your application architecture. This is another way of understanding how the CloudWatch and autoscaling also comes into the picture. Again, consider this as symbolic representation, not a production level architecture. You have an autoscaling group, and you have two servers, and then you have a load balancer on top of it, and you also think that CloudWatch is configured and autoscaling is there, and it is collecting metrics all the time. So the next step is your elastic load balancer will send the latency information to your CloudWatch, and then your autoscaling will send the utilization metric to your CloudWatch, and CloudWatch will constantly evaluate it with the rules that you have configured. And CloudWatch is a monitoring service. You can say that when CPU is this much percentage utilization, trigger a scale in event or scale out event. So let us say there is a event that has happened now, and CloudWatch is taking an action. So it will send you the execute autoscaling policy. It might be a scale in or scale out event. Even I don't know what is going to happen next. So it looks like it is a scale out event. A new server is getting added. Auto scaling is still provisioning that instance. And once it has provisioned that instance, auto scaling will send an event to your load balancer. So it will notify that I have added another server to the auto scaling group. Uh, Please be aware of the additional server. This is the IP address. This is the URL. And once that happens, then ELB will start sending traffic to the new instance as well. So that is how logically a load balancer looks like, and it distributes the traffic. So when it comes to ELB metrics, you have a lot of metrics available. One of them is the healthy host count. That means how many servers are available and how many servers are healthy. In that, it keeps count of all those things. We don't have to do anything. There is a nice dashboard. Amazon shows you, the dashboard says you have 200 instances configured with your load balancer. Out of 200, 199 is good, one is bad. So it gives you a count of that, and based on that, you can design additional actions you can take. So another metric that is available with your load balancer is latency. It measures how fast your responses are coming in, how many milliseconds it is taking to respond to your queries, and it gives you that input. And finally, there is one more metric that is coming out is rejected connection count. Say, for example, there are 200 connections that is coming in, and some 10 or 20 connections are failing or timing out. Then your load balancer keeps count of those timings, and then it informs you. So you can take all these performance metrics through an API call, and then you can trigger a scale out event or anything in your auto scaling, and you can configure your CloudWatch appropriately. So that is how these metrics are coming into picture. You can decide your scale out, scale in event based on healthy service count, healthy instance count. The second one was latency, and then the third one is a rejected connection count. So these are all the different metrics that is available for you to decide a scale out event. So now we are going to go ahead and set up this demo architecture in our hands-on demo and see how do we set it up. So logically, we are going to set up maybe 3 availability zones, maybe 2 availability zones, and in one region, and we are going to set up 2 instances which are going to be our web servers serving a small amount of web traffic, and then we are going to front end it with a load balancer. So this is the demo architecture we are going to see right now. So let's go ahead and do our hands-on demo, or if not, we can see it in the next video as well.